Welcome back. In this brief lecture, we will look at a phenomenon which is not that well understood in EDLC, but it's still important, at least even without understanding the microscopic mechanism, we will look at the ways it is addressed via certain models. So the phenomenon which we are referring to is the self-discharge. That is, if you leave a capacitor, even when it is not getting discharged, its voltage tends to go down, even under open circuit condition. This is a rather intriguing um, aspect of both a capacitor and a battery. Um, so as I mentioned, it's not completely understood, but there are some models. So the one way to think about leakage current is that it is there is a resistance to leakage current, and this resistance is in parallel to the capacitor. That is, um, even when the capacitor is under open circuit condition, there is a decrease in voltage. That is because of the leakage. So this is in parallel to capacitor. This circuit element, that is this resistor, is in parallel to the capacitor. So in a way, you can also argue leakage current is that current that you need to apply so that the voltage of a capacitor does not change. So there is another definition of a leakage current. That is, the leakage current is the current that has to be applied to keep the device at a fixed potential. So this is one way of defining leakage current. The current applied to keep the device, in this case, a capacitor, at a fixed potential. So when this is so, you can apply the current continuity condition at this node. So current is equal to applied current plus the leakage current, right? So this current is the current that is going towards this node. There are two currents that are away from this node, that is the applied current and the leakage current. You can have this general continuity condition for current. So with this definition, we can talk about the leakage current in two different ways, right? So the leakage current is the current that needs to be applied to keep the voltage constant. So I leakage times RP would be V, that is the voltage of a capacitor, or the leakage current, because of the leakage current, the voltage continues to change in a particular manner. So this is the second way of thinking about the leakage current. How does the voltage change because of the leakage current? So using two definitions, you can obtain this expression, which can be used for modeling the leakage current. There are two different models. One is shown in this slide. This is the way to think about leakage current. And corresponding to this equation, you have this behavior. Note along the y-axis, the leakage current is plotted in a linear fashion, and x-axis is the change in voltage. Corresponding to this equation, the voltage decreases as the capacitor gets, as the voltage decreases, the leakage current also decreases. That is the main feature of this behavior. That is, the rate of change of voltage is proportional to voltage. So as the voltage becomes smaller and smaller, the leakage current also gets smaller and smaller. We can also think about leakage current in a manner analogous to leakage current in a battery. This has been discussed in a previous lecture on batteries. So there were redox shuttles, certain impurity, which contribute to Faradaic reactions, unwanted Faradaic reactions in a battery. So similar mechanisms can be envisaged in a capacitor too. So then you can, so there are many different um, reasons, right? So one of the main point in a battery when there's a dramatic self-discharge is via electrical shorts. Okay, so and there are other ways. These are the two other ways which we thought through. So in the absence of electrical shorts, we can think about Faraday reaction. We assume that the Faraday reactions that contribute to leakage current in an EDLC forms the expression for that leakage current can be approximated via Tafel kinetics. Okay, so the O potential is large enough, and if the O potential is large enough, you can assume Tafel equation to represent the Faraday reactions that contribute to leakage current in the EDLC. So if you assume this kind of a behavior, the leakage current shows this kind of a drop. That is, note, as opposed to this linear change in the x-axis, here it is goes in look the range is very different in this axis as compared to the leakage current in this axis. So if you assume this form of leakage current corresponding to this way of plotting the leakage current, you get this expression. So what is the main difference? In this difference, in this behavior, that is assuming these two are some kind of Faraday reaction that contribute to leakage current of EDLC, the voltage does not change that significantly when the leakage current changes. So there is an order of magnitude difference in the leakage current corresponding to this change in leakage current. The change in voltage is not that much. So there are two different behaviors. So as I had mentioned, the microscopic mechanism of self-discharge or leakage current in EDLC is even less understood compared to self-discharge in a battery. So at least there are two general models, and the two models give fairly different behavior for leakage current and how does the leakage current affect the voltage of a capacitor. In the next lecture, we will look at an important topic, that is the pseudo capacitance in a capacitor. Thank you.